So page 65, number 5, we have a rectangular box, no lid, constructed from 12 square meters of cardboard. It's rectangular, so we're not going to assume that the two sides are congruent to one another, so I called it x times y equals 12. Right. So if I'm going to find the volume is equal to length times width times height. So essentially I'm cutting out the corners. You know, you're familiar with this from every other math class you've ever taken in your lives. That's an exaggeration, but not too far off. We would fold up the sides, and we would end up having some kind of height that we're not aware of at this point, and a length and a width. Right? So it appears that whatever we call the length of each of these squares is going to drive whatever the dimensions are of the box. All right, so this by whatever the height is associated with the length of that square. All right, so I'm going to need another variable in order to accomplish this. All right, so we have that relationship, x times y equals 12, which means that x is equal to 12 over y, and y is equal to 12 over x, either one. So immediately I can swap out one variable for another, which is great. But I still need another variable to represent the length of the side of a square, so I'll call that z. All right, so I have 4 squares, each having 4 sides, but I only really need to label 2 of them, equal to z. All right, the overall length is x, and the overall width is y. So this side here, we could call x minus 2z. And this side here I can call y minus 2z. All right, so I could say v, I'll leave the of part out, like of x, of y, of whatever. I'll leave that off for a second. We're going to say x minus 2z, y minus 2z, and h would just be z. All right, so this is v of x, y, z, which would be a function of 3 variables. But we do have a relationship that allows us to pare this down. All right, so I can write it as v of x, y, z now, but I'm gonna streamline it in a second. All right, so make a little note there. So it's just decide which one do you like. I think I like x. So I'm going to replace the y with an expression involving x. All right, so copy paste. Over x goes in for the y. All right, so now it's a function of 2 variables, so I can chop out that little y there, get rid of that, and now it's a function of x and z. A little bit easier. Not like a bazillion times easier, but easier nonetheless. All right, we can distribute it out and then combine some like terms. All right, so that's next on the list of things to do. I'll save the z for last. So I'm going to distribute the x against these 2 guys. You highlight everything, it's like you highlight nothing. So 12 minus 2xz. Then I'm going to multiply through with the negative 2z. So that's going to give me a negative 24 z over x plus 4z squared, and all of that is getting multiplied by z. All right, so 12z minus 2x z squared minus 24z squared over x plus 4z cubed. All right, so a lot of funkiness going on here, but it is a multivariable function, and so that's part of the fun. All right, so we just got to kind of grin and bear it here. So let's get our first order partials. I'll just kind of, I'm going to use my drawing tool here, or writing tool. So v sub x. Well, I guess before I do that, I probably want to write this slightly differently. Let me go back here. Just to make life a little bit easier. And you know, let me smidge this down in scale. Move that. I'm going to bring this guy up and give it a power of -1. This gives it a little bit more of a cleaner look, which is going to make things a little easier when it comes to simplifying and so on. All right, so now we'll experience the full power of the dark side. So we're differentiating with respect to x, and then z, and then we'll get our second order partials and all that good stuff. So let's take care of that. Get rid of this. All right, so the 12z goes away. The second term, I'll highlight it real quick. The derivative of x goes to 1, so everything else stays put, so -2z squared. The derivative of the -24x to the -1st, blah, blah, blah. Well, the x to the -1st becomes -x to the -2nd. All right, so we'll make that a plus 24 x to the -2nd z squared. All right, so that makes life a little bit easier. The first order partial isn't that bad. You know, the mixed partials will be a little funky, but you know, it's still polynomial, or at least power function relationship. It's pretty clean. So we're looking at 12, and then we would have, if we're taking the derivative of the -2x z squared, it's really the z squared becoming a 2z, so -4 xz. Same deal here. I mean, if we tried to combine like terms, I'm sure we could in some way, but it'd make things a little messier. So 48, -48 x to the -1st z, and then plus 12z squared. All right, so we have our partials. Now I just need my second order partials of the mixed variety. So I'll get my v sub xx. All right, really the only thing that's relevant here would be this one. So we're looking at, excuse me, we're looking at -48 x to the negative third, and then we'd have z squared. And I can get my second order, I almost put a y, mixed partial just with respect to z. All right, so negative 4z, and then plus a 48 x to the negative second, z to the first. All right. So then I can take care of my second order partial with respect to z. Constants go away. We're looking at negative 4 minus 48x to the negative first plus 24z. Not too bad. My second order mixed partial. Now I'm just doing this to verify that I didn't just screw up v sub xz. So this part is not necessary, but you know, I don't want to take the chance. So if we're taking the derivative of this one with respect to x, constant still goes away. So this would become negative 4z. Then I would have a positive 48 x to the negative second z. And then anything with a z in it would go away, so that would zap away. All right, so I got what I got before, so I'm feeling pretty good about that. All right, I'm going to shrink this down. All right, so I got a lot more information than I needed to find my critical values, but I'm going to need to find that stuff anyway. So now I'm going to go through the process of finding those criticals. Every 2 seconds I get a new one. Every 2 seconds. I really wish that was an exaggeration. It is not. Okay, so we have v sub x needs to be set equal to 0, and v sub z needs to be set equal to 0. So I'm going to I'll get rid of the highlighting here. And then v sub z also going to be set equal to 0. All right, so a little bit of work ahead of us algebraically, but you know, at least it's algebra. We can handle algebra. It's just going to take some doing. All right, so again, we have those like terms. So what I can do here is I can just, so I'll focus on this guy. I got a common z squared that I can factor out. So let's take care of that. So negative 2 plus 24, and I'm going to write this as over x squared equals 0. So I'm going to get z equals 0, and I'm going to get negative 2 plus 24 over x squared equals 0. Now that we can treat, I mean, it's a rational function, so I can distribute through the x squared, so make it negative 2 x squared plus 24 equals 0. You do it that way. Ultimately, we're looking for a solution, so if you want, just go right to Desmos. Type in negative 2x squared. I mean, it's not too difficult to divide. It's going to be the square root of 12, I think. But yeah, if you wanted to just go into Desmos and do it, you could do it that way too. All right, so you get this solution here, funky decimal. You're like, what is that funky decimal? You know, you can square it and see, because you figure if it's a result of a quadratic and it's a funky decimal, you got to figure it's the square root of something. So find the square root. But if you don't like that, then you can just subtract, divide, you get x squared equals 12, which means that x is equal to plus or minus root 12. And you can just verify. All right, so that's your 3.46-ish. All right, positive or negative. So we have some values. Now these aren't corresponding values, as in this is not going to give us an ordered pair, because this x doesn't correspond to that, or this set of x values doesn't correspond to that 0. All right, so what we can do, because again we have an equation with two variables, or two equations with two variables, is we can go into our second equation and replace all of our z's with 0. So I'll highlight that. All right, and when I do that, you know, just going right through and saying, okay, let z equal 0, you run into a contradiction. All right, so that contradiction, it's, you know, I mean, in the grand scheme of things, you might say, well, I really wish that didn't happen. But, and that's because it's a nice clean number, the 0. You want 0 to work out. But the bottom line is, well, it would have led to another solution anyway. So it's for the best, I guess. So we know that z is not going to amount to anything. So you toss that one. So what I'll do now is I'll replace all the x's with plus or minus radical 12. We'll try to do it all in one shot at first, but then we'll definitely have to split it off and work it out from there. So 12 minus 4 times plus or minus root 12 z minus 48. I'm going to write this over plus or minus the square root of 12 z plus 12z squared. All equal to 0. All right. Since it's quadratic, I can get it into, you know, standard form or general form, sorry, for a quadratic. I have these two terms in the middle that kind of make things a little dicey, but I can just kind of maneuver things around. And really, in the end, it just kind of amounts to swapping this term with this term. You know, not too complicated when you think about it that way. All right. So now it does appear that we have to account for the plus or minus 12 as two separate equations, or giving two separate equations. So we'll do that. We'll focus first on the negative first. So we're looking at 12z squared. Two negatives make a positive, so plus 4 radical 12z. Two negatives make a positive, so plus 48 over radical 12z plus 12 equals 0. All right. We can trim that down a little bit more because, again, we have that common factor of z. So we could factor that out. Well, really, just kind of factor it out, but leave it at the end of the binomial. So we'd be looking at 12z squared plus 4 radical 12 plus 48 over radical 12 z plus 12 equals 0. All right, so I have a quadratic. That's great. Now, all of this is assuming that you don't want to do it using Desmos. I think I've probably sold everybody at this point that Desmos is probably the way to go, because, you know, you'd have to get into quadratic formula, completing the square or something like that, and when all is said and done, you're going to end up with a nasty answer anyhow, most likely. So why not, why not let Desmos give you the nasty answer? And if it's not nasty, then you could probably pick it out from Desmos anyhow, right? So, we can get into, getting a common denominator and stuff like that. If you want, use Desmos to see if it can help you simplify a little bit. I got a 4, that's not a 4, 4 radical 12 plus 48 over radical 12. And that's 27 point something or other. See what happens if I square that. It's the square root of 768 is what that amounts to. All right, so from there you can go through the process of trying to simplify and see where that gets you. But that's up to you. I'm going to go a different way. I'm going to say that this is 12x squared plus 4 radical 12 plus 48 over radical 12. Again, not an algebra class. Keep that in mind. Rule of thumb. Plus 12. And I'll say that that's equal to some function that I'll call f of x. Probably should have wrote the f of x in first. All right, so there's my function, and that's going to spit out some values for z. All right, so I actually get two solutions, and they're surprisingly not bad. All right, so z gets these two decimal values, but if you're familiar enough to know that those are unit circle values related to tangent. And you should be familiar enough to know because we've done that with the unit circle bonus problems. All right, so anyway, one of them is negative radical 3, and the other is negative radical 3 over 3. All right, the issue is here, if you haven't noticed, those are negatives. That's kind of a problem. It means that what we just did was a complete and total waste of time. No, it just means that this is probably not the solution that's going to be most meaningful for us. Now, if you kind of read into the context of the situation, so x is a dimension. That dimension should be positive, right? So we never really should have taken into account the negative anyway. But, we play it out and we see where it goes. So regardless, we can still kind of carry on from here because all it's going to do is impact the signage, right? So we just took care of the train of thought. We took care, and I don't want to highlight everything here. We took care of the negative case. So let's take care of the positive case. All right. So that positive case would give us a negative here and a negative here, which is going to influence the sign in front of the binomial to be negative. So not much change, because from there I can just say or. Go into my Desmos, change that plus into a minus, and you see we get the same values. And actually, I don't even need the or. I'll just do it like this. So plus gave you a minus. I'll move that up. Minus gave you a plus. All right, so I'm looking at two possible results here. All right, z could be equal to radical 3, or it could be equal to radical 3 over 3. All right, it's not going to be equal to both. In order to give us the maximum volume, which seems to be what we're looking for, it's going to be equal to one or the other. All right, so that's really the question. Which one's going to get the job done? All right, will a taller box, aka the radical 3, get the job done, or will a shorter box, the radical 3 over 3, get the job done? All right, so that is the big question, and we have to analyze that. So we have our critical values. That took a while, but we got there. Now what we need to do is analyze those critical values using the second derivatives test. All right, so what I'm going to do is get all of my good friends here. V sub xx, yy, v sub xx, zz, and the mixed second order partials. So I'll jot that down somewhere over here. Yeah, just check it in over here. V sub xx, V sub zz, V sub xz. And this is at, what was the ordered pair? Radical 12. Let's see, just making sure the negative radical 12 was the irrelevant one, so we're only looking for positive case. So radical 12, comma, radical 3. Well, comma, V of radical 12, radical 3. So I need those values, and then I need my discriminant. And then I need to do the same thing again, just with a radical 3 over 3, but one thing at a time. All right, so let's reference our functions. I don't really need that anymore, I don't think. Hopefully I won't regret that. I'll bring it back in so I don't regret it, but I'll turn it off so I don't have to look at it. So negative 48. I'm going to go with an a for the x. So a to the negative third. And z squared, so b squared. Get some sliders in there, move this down, because I'm going to be using a and b over and over again. All right. Then I want my yy, in this case zz. So negative 4 minus 48, a to the negative first, plus 24 times b. That's my zz. And then they mixed, so zx or xz would be negative 4, z is b, plus 48, x to the negative second. I did it. I knew I would do it at some point. X is a. Multiplied by b, which is taking on the role of z. All right. So for this one, I want to go right down the line, replacing my a with a radical 12. n my b with a radical 3 and see what that gives me. All right. So we get some negative values here, and that's all right. All right, so we're looking at negative 3.464 approximately. ZZ is 27.713. XZ is equal to 0. So the D is just going to be the product of these two values. All right. So we're just looking really for the sign, right? So XX times ZZ minus XZ squared, that's going to be a negative result. Barring any catastrophic computational errors. Just double checking. Yeah, negative 3.464. It's just that second value looks a little on the big side. I'm worried that I typed something in incorrectly. Ah, there it is. My ZZ. The derivative, I guarantee somebody was screaming at the screen. So taking the derivative of this with respect to z should have been negative 4x. All right, that's going to make things better. This should be a wrong one. Yeah. Yeah, it looked a little big. It's like, where'd that number come from? So 13.856 approximately. All right. So when we look for the discriminant here, again, it's the product. Oh, it's just something still feels a little off. With respect to z. No, okay. It felt wrong, but I think it's all right. All right, well, regardless, it's going to be a negative. All right, so that's one set of computations. So let me find some room for that. And then I want to do the same thing, but this time it's just radical 3s. And that's the power of the Desmos approach to things, because minor adjustment here, and we're looking at about negative 0.385. And then for the ZZ, it would be about negative 13.856, so just slap a little negative on there. Still a 0. All All right, so this one would be positive. Okay, so, you know, if you reflect back to the rules for the second derivatives test, if my discriminant is positive, then we're talking about possibility for local extrema. If it's negative, then you're looking at a saddle point. So I'm not really interested in a saddle point, but if I were, it appears that I have a saddle point when the x and y, x and z values are equal to radical 12 and radical 3 respectively. All right. So that's something. Now, it looks like this guy is going to be the winner. It's just a question of what does that tell us? All right. So we have a negative second order partial with respect to x. So v sub, and I can actually kind of chuck that in here. You know, let me do a better job of chucking it. So we're looking at a local max. So we have all the dimensions that we're going to need for this, which is great because it's all kind of hidden right in plain sight. All right. So I have, again, an x value. Let me just kind of annotate this. Here's my x. Here's the z. And this is just going to give me the volume. They're asking for the maximum volume that such a box can have. All right. So whatever variation of the form that you want, you can go for it. But I prefer to kind of list out what the dimensions would be, even if they don't ask it. So x, radical 12, z, radical 3 over 3, and y, well, 12 divided by radical 12 is going to be radical 12. So coincidentally, turns out that this thing actually was a square, but we didn't know that going in. All right. And the benefit of doing it this way is I don't actually have to go to my volume formula in order to figure out what the volume of the figure is going to be, because I can just subtract off the dimensions and multiply if I want. But we have a formula, so why not, So we're looking at, again, x minus 2z, y minus 2z times z. All right. So x minus, parentheses, and it's only the one computation, so I could just pop it right in, x minus 2 radical 3 over 3 all right. Oh, actually, we know what x is, which is really weird after all this. Radical 12 minus 2 radical 3 over 3. Two of those, right? So let's just square that and multiply that by radical 3 over 3. All right, and so that's going to give us the maximum volume. All right, so the dimension, the z value, the dimensions in general, we're talking about meters. So meters, 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 max volume, approximately 3.1 square meters. All right, so we know the dimensions that the cardboard have to be in order to give the max volume, and we know what size the notches need to be cut out at in order to give that max volume. All right, so a lot of good stuff going on here. Just, you saw, look at this. all this work we had to do and all the shrinking down of everything. There's a lot of work involved. All right, so that's where we're going to leave it for that.